Next topic we have to discuss is heat generation in metal cutting. So based on the first law of thermodynamics, the energy supplied mechanical energy, is converting into heat energy. So heat energy is converting from one form to another form. That's first law of thermodynamics, where heat supplied is equal to the change in internal energy and work done. Heat supplied equal to, here heat supplied in terms of power supplied to the tool. So power supplied is work done by the tool, and as well as heat generated, internal energy. So here the heat generated at different zones between workpiece and tool, and between tool and the chip, and between chip and the workpiece. So there are different zones. We need to discuss how much heat is generated at each zone. Suppose in any metal cutting, this is especially single point cutting tool is used. Workpiece, and this tool, this is chip. Just layout diagram to understand the concept. This one is one zone, and another zone is this one, and this one is another zone. So first one is called, this one is primary, this one is secondary, this one is territory. Short form I am giving notation. So primary heat zone, first one is primary heat zone. So primary heat zone here is due to the breakage of atomic bonds. See, whenever the tool starts moving, that means if it starts moving material removal, so the solid part, the chip has to come out from the solid part. So that means there is a breakage of atomic bond. So because atomic bond is breaking, means a lot of energy is getting released. So a lot of heat is generated there. So atomic bond between the atoms of the material is getting broken. During this time, atoms are releasing a large amount of energy in the form of heat energy. Due to breakage of atomic bond, the breakage of atomic bond between the atoms of the material, there is large amount of energy is released. This energy is this heat energy is about 65% of the total energy generated. And generated in metal cutting. So we have here three zones: primary, secondary, tertiary. So out of the three zones, in primary zone 65% of the total heat generated in all the combining all the zones is generated here. So out of this 65%, out of the maximum amount of energy is carried away by chip. Out of the 65% of heat, maximum amount of heat is carried away by chip, because chip, once it gets heated up, it once chip starts forming, it goes out, and anyway we are generally prefer discontinuous chips. The chips breaks and go out, like from the workpiece. So while going out, they carry the heat, because the chip carries the heat, and the minimum amount of heat is carried away by workpiece. So maximum amount of heat is carried away by chip, and very minimum 10% or something, and minimum amount of heat is carried by workpiece, means absorbed by workpiece. So workpiece will get heated up. So that is a primary heat zone. Next one is secondary heat zone. So secondary heat zone, what happens in secondary heat zone? Secondary heat zone, the heat is generated because of the friction between the chip and tool interface. The heat is generated due to friction between chip and tool. So friction between chip and tool interface, heat is generated in secondary zone. It's about 25 to 30% of the total heat generated. So energy lost in friction, it's also called. So maximum amount of energy, heat is taken carry by chip. A small amount of heat is carried away by tool. Maximum amount of heat is carried away by chip, and minimum by tool. So that is about the secondary heat zone. The friction. Third, next one is tertiary heat zone. Tertiary heat zone, heat is generated due to friction between tool and workpiece. So it's about 5 to 10% of the total heat generated. So maximum amount of heat is carried by workpiece here, and small amount of heat is taken by tool. So here maximum amount of heat is taken by workpiece, and minimum amount by tool. So whatever the heat is generated in the three zones will be carried away by the three elements. So overall the heat generated in all three zones is carried away by three elements. Three elements are called chip, tool and workpiece. So if the convection and radiation losses are negligible, out of this, chip is carried away by maximum amount of heat. Next is workpiece, least is 2, because we are neglecting the radiation losses. Neglecting radiation losses, so heat carried away by chip greater than highest heat carried away. Next is workpiece. Next is tool. So chip carries 70 to 75 heat of the total heat, and workpiece is 50 to 20% of the total heat, and tool is 5 to 10%. So total amount of heat so overall the chip carries total more amount of heat, and next is workpiece, and next is tool. Why it has to be like this is because if the tool carries more amount of heat, it failure takes place early, because if heat is heat is absorbed more, means it goes deformation. And workpiece also same. So if the workpiece is taking, means tool also will take automatically. That's why the heat generated has to go out with the help of chip, because chip is moving out. So because chip is carrying away maximum amount of heat, rising temperature of chip is very high. The heat carried away by chip is maximum, so the temperature of the chip is also maximum. So total work done equal to heat carried away by chip plus heat carried by workpiece, neglecting heat carried by tool. So total work done is W equal to heat carried away by chip is Q chip plus heat carried away by workpiece is in terms of W, A equal to the fraction of heat generated will be carried away by the workpiece. W equal to Q chip plus AW. So Q chip equal to W into 1 minus A. Q chip is nothing but MCP delta T equal to W is work done is equal to the force into velocity 1 minus A. So MCP delta T is temperature difference, heat temperature rise in the chip, equal to FCVC 1 minus A by mass is MCP. Mass is nothing but density into volume. Okay. So delta T is nothing but rise in temperature of chip. Next is tool life. It is one of the important topic. Most of the times you will get 2 marks, minimum 4 marks also linked answer questions. Tool life actual meaning is actual machining time between two successive regrinds of a cutting tool is called tool life. Machining time between two successive regrinds of the cutting tool is called tool life. Tool life is generally specified in terms of minutes. tool life is specified in minutes. So it also has different definitions, like number of components produced between two successive regrinds is called tool life. Another definition is number of components, like number of products or components produced or manufactured between two successive regrinds is called tool life. Another definition is volume of material removed between two successive regrinds. So in different ways of explaining. So if you look at the three definitions, the common thing is between two successive regrinds I bought one tool and I used for it for some time, and it become blunt, and I again went for regrinding to sharpen the tool. So the time it took, for how much machining time it has, the tool is used before regrinding or between two successive regrinds is called tool life. Generally it always represented in minutes. Factors which are influencing tool life. Generally properties of workpiece material affects the tool life. Suppose if the hardness of the workpiece material is high, tool life will become lower. Higher the cutting forces, tool life will be lower. Higher the tool wear, the tool life will be lower. Tool life has different definitions. So tool life, the tool life tool depends upon the hardness of the workpiece and cutting forces developed in the machining. So use of coolant increases tool life. Like process parameters, velocity, feed, depth of cut having highest also influence the tool life. So those we will discuss in the Taylor's tool life equation. Taylor's tool life equation tells us relation between the velocity and the tool life. Vt power n equal to constant. V equal to cutting velocity or relative velocity between the tool and workpiece in motion, meter per minute. T is tool life in minutes. N is Taylor's exponent. C is Taylor's constant. So this is as velocity increases, tool life decreases, but it is not like directly or inversely proportional. So the depends upon the exponent's value depends upon the type or material of the tool. Sorry. So there is another, actually even tool life depends upon the feed and depth of cut also, but it mainly depends on the velocity of the cutting tool. So there is another tool life it extended to the feed and depth of cut, that is equal to the Taylor's tool life considering feed and depth of cut. F equal to feed in m per revolution, D equal to depth of cut in mm. So the impact of the three parameters, like which has more impact on the tool life. So impact on tool life is velocity has more impact, then feed, and then depth of cut.